location in three-dimensional space can be described with three numbers. So in Cartesian coordinates, x, y, and z, I'll put up a set of axes here. We would usually just use those three numbers, x, y, and z. And so if I wanted to think about some point P over here in space that has some distance x that it's at along the x-axis, some distance y that it's at along the y-axis, and then also some distance z that it's at along the z-axis, I could just write this as some location x, y, and z. And you guys are all probably familiar with this. Sometimes we'll be working in geometries that call for a different set of three numbers. So for example, let's think about if I have a circle, and maybe it's a disk. So it's a disk of charge. And I want to describe the location of some piece of this disk of charge. So let's say that this is my origin. So let's say that I'm looking at the xy plane here. So I've got an x-axis and a y-axis, and I have some point P in space over here. Now this point P is still clearly described by x and y, but another way I could describe it is I could describe it as the distance from the center of the circle, which in this class we will call eta. This is a Greek letter, eta, and the angle that this line makes from the x-axis, which we will call phi, which is another Greek letter. And so it's still two numbers, right? Instead of x and y, now it's eta and phi. But an advantage of this is that a lot of the time when I'm thinking about this disk, I really just want to know how far away am I from the center of the disk. And if I'm working in Cartesian coordinates, then my distance from the center of the disk is going to be the square root of x squared plus y squared. Whereas if I'm working in cylindrical coordinates, that's what these are called, then the distance from the center of the disk is just eta. And so you can see that by working in the natural coordinates of whatever geometry we're operating in, we'll be able to simplify mathematical expressions significantly. So there are two alternative geometries we'll be dealing with frequently in this course. There is cylindrical geometry, and there is also spherical geometry. So in cylindrical geometry, I've already given you two of the coordinates that we tend to work with. We'll work with eta, the distance from the center of the cylinder, and phi, the angle from the x-axis. But also, if we wanted to think about, instead of just a circle, which is a cross-section through a cylinder, if we wanted to think about an actual cylinder that also has a height, then we would want to add one additional coordinate, and that would be z. So the distance that you are within the cylinder. And so if I have some cylinder like that, let's say that my x, y, and z axis is located at this bottom coordinate, bottom left corner of the cylinder, then our z coordinate to describe some location within the cylinder P is just going to be the same as our Cartesian z coordinate. But then, well, I drew this P right at the center of the cylinder, so let's draw this P a little bit off the center of the cylinder. So this location P is going to be described by some value z, some value eta, which is the distance that it is from the center of the cylinder, and then some value phi, which is how far it is rotated off of the x-axis. And the way I've drawn this, we can't really see it, but I could imagine cutting a cross-section through this cylinder, and that's just what this would be. So we can define our phi angle in cross-section of the cylinder. For spherical coordinates, oh, actually, before we go into spherical coordinates, let's also discuss the ranges that these coordinates can So x, y, and z all go from negative infinity to minus infinity, right? We have a negative x-axis, we have a positive x-axis, and they extend on forever. So for x, y, and z goes from negative infinity to positive infinity. For eta, phi, and z, the situation is different. So z can still go from negative infinity to positive infinity. I'll just purchase some space here. So this is in Cartesian. In cylindrical, we have our z coordinate, which can still go from negative infinity all the way to positive infinity. But then we have our eta coordinate and our phi coordinate. So eta is just, remember, measuring the distance from the center of the cylinder to wherever we're interested in. And so eta can go from 0 to positive infinity, because it's just a distance. So we can never have a negative distance to the center of the cylinder. So it's either 0, you're right at the center, or some positive number. And then we have phi, and phi is the angle measured from the x-axis. And since it makes a circle, phi is going to run from 0 to 2 pi. And that's the range of possible values for that angle. Now, for spherical coordinates, they're going to be somewhat similar to cylindrical coordinates, but a little more complicated, because now we're operating in a geometry where we can't sort of cheat and carry forward one of our Cartesian coordinates. So if I am thinking about a location in a spherical sense, so again, I'm going to draw my normal Cartesian axes, x, y, and z. And now I'm interested in some point P, but I want to describe it in terms of a sphere. So let's say that there is, in fact, a sphere, and let's just imagine that I drew this such that the center of the coordinate system is actually at the center of the sphere. Then we want to describe how far is P from the center of the sphere. Here we're going to use r instead of eta to describe how far it is from the center of the sphere. We also want to describe where it is in relation to the top of the sphere, and we will use an angle theta, another Greek letter, to describe the location of this point with respect to the top of the sphere. This is called the polar angle. And we again want to describe where point P is in relation to the x-axis, and so we'll also use phi for that. So we can imagine that this point P has some projection down into the xy plane, and so it exists at some angle phi with respect to the x-axis, and phi is often called the azimuthal angle. And I just want to show you on a physical object what the polar and azimuthal angles are, because I think they can be confusing. So this is my sphere, and this is the top of my sphere, and by convention we will say that the top of the sphere is along the positive x-axis. So we always measure our polar angle, or almost always, from the positive x-axis. So the polar angle is the angle that goes down like this along the side. So it starts at 0. So right at the top of the sphere, the polar angle is 0. When we get to halfway down the sphere, the polar angle is pi over 2. And then when we get to the bottom, it's pi. So that's the direction of the polar angle. The azimuthal angle goes around in this direction. So let's say that the positive x-axis is right here on the sphere. then the azimuthal angle is going around the sphere in this direction. So this location, the azimuthal angle is 0. Here, it's pi over 2. Here, it's pi. Here, it's 3 pi over 2. And over here, it is 0 / 2 pi. So if we want to write down the ranges in spherical coordinates, I've sort of already said them, but I'll just write them here for completeness. R, just like eta, can go from 0 to infinity because it's describing the distance from the center of the sphere, so it can't be negative. Theta goes from 0 to pi. That's the polar coordinate. We don't have it wrap around. So if I'm measuring a point P that's on the other side of the z-axis, then we just define the polar angle from the z-axis again, not from one particular side of the z-axis. And then phi goes from 0 to 2 pi again. So phi in cylindrical and spherical coordinates is basically the same. It's the azimuthal angle in both situations. So just like any location can be described with 3 numbers in 3-dimensional space, it is also the case that any direction can be described with 3 numbers in 3-dimensional space. So instead of imagining that this is a point P, now let's imagine that it is a vector P. And so it has both a magnitude and a direction. Now in Cartesian coordinates, we would usually describe this direction in terms of the I, J, and K components, which in this class we will also sometimes call the x hat, y hat, and z hat components. And these are just describing what proportion of the vector is pointing in the x, y, and z direction. Now, in spherical and cylindrical coordinates, again, we're going to need 3 directions, but they're not just going to be the x, y, and z directions. So if I have a sphere, for example, so let's say here are my Cartesian axes, but now I again have my vector P, but we're going to say that this is in some spherical geometry. So now it's going to have an r hat, a theta hat, and a phi hat direction. So the r hat direction is just the direction that's pointing directly away from the center of the sphere, so from the origin, essentially. So in this case, the r hat direction points immediately away. The theta hat direction points in the direction of increasing theta, which is to say that right here, theta points in this direction, and you just sort of imagine sliding down the surface of a sphere. So here, theta would be pointing in this direction. So theta is pointing along the polar direction of the sphere. So at the top of the sphere, theta is pointing in the positive x direction. Right here, theta is pointing directly down. And at the bottom of the sphere, it's pointing, again, directly perpendicular or along the x-axis. Now there's one other direction, which is the phi hat direction. And the way I have drawn this, phi hat would be pointing directly into the board. And phi hat is very similar to theta hat, except it's in the azimuthal direction now. So it points along the surface of the sphere as you increase phi. So in this case, I will just draw it as a little x with a circle to indicate a vector going into the board. But now I'm going to, let's see, I'll use a different color to draw a projection. So I'm going to draw a projection of the xy plane at this location. So if I do that, so I've got x and y, and here is my vector P. Here is my azimuthal angle phi, and here we can see that phi hat pointing in this direction when we project it down into the xy plane. So you can see that just like I, j, and k, or x, y, and z hat, are perpendicular to each other, r hat, theta hat, and phi hat are also perpendicular to each other. Oh, I forgot to label phi hat there. And so just with those three numbers, you're able to fully describe the direction of a vector. Finally, in cylindrical coordinates, we're going to have a phi hat that behaves very similarly to the phi hat in spherical coordinates, and we're going to have, instead of an r hat, an eta hat that behaves very similarly to r hat. So in a cylindrical geometry, let's see, we have our cylinder here, and we have some, let's say that this is our origin, again in the bottom left-hand corner of the cylinder, and we have some vector p. Then this vector is going to be described by a z hat direction going along the direction of the cylinder, an eta hat direction that's going away from the center of the cylinder. So for this cylinder, eta hat points in this direction when we're on this side of the center axis of the cylinder, and eta hat would point in this direction when we're on the other side of the center axis of the cylinder. And it also has a phi hat direction, which again is easiest to see if we take a projection of the cylinder into the xy plane, and then it would look exactly like this. So one thing you may have noticed while I was describing r hat, theta hat, phi hat, and eta hat, is that they keep changing direction. So with x hat, y hat, and z hat, at every point in space, they are pointing in the same direction. So at this location, x hat is in this direction. At this location, x hat is in this direction. Over here, x hat is in this direction. And so the directions that we're using to describe vectors, so the different components, are always pointing in the same direction. For cylindrical and spherical coordinates, that is not the case. So, for example, here, at this point, eta points in this direction. But over here, eta is pointing in exactly the opposite direction. For phi hat points at this direction right here, so it would be pointing down and to the left over here. And so the fact that these components keep changing direction, depending on where you are in space, means that while they are still useful for describing a vector in cylindrical or spherical components, they are not useful for adding vectors together, right? So if I have one vector p1 over here, and then let's say that I had another vector p2 over here, if I added those phi hat components together, as I was adding the vectors together component-wise, I wouldn't get something that made any sense. So when you want to add vectors together, you have to use Cartesian components, that is ijk or x hat, y hat, z hat. So in this course, something that is often useful and something we'll be doing very frequently is to write down vectors in Cartesian components, but in cylindrical or spherical coordinates, which is to say that we would write something as having x, y, and z components, but instead of using x, y, and z in those components, we would use r phi and z, or sorry, eta phi and z, or r theta and phi. So I will show you what I mean. If I have, let's say, a sphere, and so I'm going to put up my Cartesian axes, as usual, x, y, and z, and then I have some vector p that I want to describe, and let's say that this vector is somewhere within a sphere, and so it's useful to use spherical coordinates to describe this vector. but I want to describe it in Cartesian components because maybe I need to integrate over this sphere. And remember, integrals are just sums, and so if you're integrating, you definitely want to be in Cartesian components so that you can add up all your vectors appropriately. So in order to do this, I need to find the x, y, and z components of this vector in terms of r, theta, and phi. And so for z, it's not too bad. So in the z direction, remember we have this polar coordinate theta, and we know that the length of this vector is just r, the distance from the center of the sphere, and we've put the origin of our coordinate system at the center of the sphere. And so take a minute, maybe pause the video and see if you can decide what this distance is. So we can see that this distance is just going to be r cosine theta, which is to say that the z component of our p vector is going to be r cos theta. Now, if we wanted to project this vector down into the xy plane, we can see that this projection is just going to be r sine theta. So now let's look at the vector p projected into the xy plane so that we can find its x and y components. So we'll, again, do our projection in pink, or actually, we're projecting the vector itself, so we want to project it at this level. So I will uncomplicate this a little bit. We have our vector p, and it has a length r sine theta. Why does it have a length r sine theta? Remember that this is the projection of this vector down into the xy plane. And so in a sphere, let's say that this is occurring somewhere in this part of the sphere. At this part of the sphere has a smaller radius, a smaller radius if you're just considering a cross-sectional circle. So if we're considering a cross-sectional circle of the sphere, it has a smaller radius, and so that radius is described by r sine theta. So let's say that the sphere has a total radius of a. Then when theta is pi over 2, which is to say when sine theta is 1, this is just the whole radius a. But at the very little bitty top, if you projected a vector that was pointing straight at the top of the sphere into the xy plane, it wouldn't have any length in the xy plane. So that's what this r sine theta is capturing. So in the xy plane, this vector has a length r sine theta, and then if we want to find the y and x components, we again just need to use some trigonometry. So we see that this distance is going to be r sine theta cosine phi, and this distance is r sine theta sine phi. And so if we want to write our vector in spherical coordinates, but in Cartesian components, then I'm just going to steal a little space here. We can write that as p equals r sine theta cosine phi x hat plus, I'm just going to move to the next line, r sine theta sine phi y hat plus r cosine theta z hat. In cylindrical coordinates, the situation is going to be a little simpler. So if I'm considering a cylinder, and I want to find the x, y, and z components of some point P, let's say, in this case, I'm going to, just for convenience, put my Cartesian coordinates at the center of the cylinder. This will make the components a little clearer. And we're considering some vector p over here. Now, the z component of vector p is just going to be z. Oh, sorry, I guess this should be over here with spherical. Let me rewrite that real quick just for clarity. Okay, so let's say that we have some vector p that's within this cylinder, and we will start writing our vector out similarly to how we wrote the spherical one. So for the z component of this vector, it's just going to be z, because we're just using the Cartesian coordinate z in our cylindrical coordinate system, and so that part is quite simple. Now, for the projection into the xy plane that we want to do to find the x and y components, our task is going to be a lot simpler than in the spherical case, because remember that our cylindrical coordinates are eta, phi, and z. Phi is defined in a very similar way to the spherical phi, in fact the same way, but eta is a little different from the spherical r, because eta is actually already a projection into the xy plane. Eta is just the distance from the z-axis, right, from the center of the cylinder. So you can see that when we draw our vector p in the xy plane, it just has a length eta. No need for there to be a sine theta or anything. It's just a length eta, and that means that the x and y components of this vector are just going to be eta, let's see, this is phi, cosine phi, and eta sine phi. And so we can write our vector p in cylindrical coordinates, but remember Cartesian components, as eta cosine phi x hat plus eta sine phi y hat plus z hat. And so in general, very frequently in this course, we're going to be using Cartesian components, x, y, and z components, but as I've written here, the cylindrical or the spherical coordinates when we're handling things in cylindrical or spherical geometries. To finish this off, I want to talk a little bit about infinitesimals, which is to say very small lines, areas, and volumes, or lengths, areas, and volumes in Cartesian, cylindrical, and spherical geometries. So a lot of the time we want to break up some longer line or bigger area or larger volume into itty-bitty pieces so that we can use it in an integral. And so, for example, if I have a very long line along, let's say, the x-axis, then I could break up this line into a bunch of little chunks, each of which has a length dx. So we use this d to indicate very small amount in that, along that direction or along that coordinate, essentially. And so then let's say that this was some line of charge, and so at each of these locations dx, there's a little bit of charge dq, and I'm trying to find the total force from this little bit of charge dq on, or the force from this little bit of charge dq on some test charge over here. So this is the little bit of force due to this little bit of charge. And then I would add up all the little bits of force due to all the little bits of charge along the line to get the total force on the test charge. So these are the sorts of circumstances in which we want to break things down into little bitty pieces. So in Cartesian coordinates, where we have x, y, and z axes, we can have a little bit of x direction dx, a little bit of length in the y direction dy, and a little bit of length in the z direction dz. And so these are all of our line elements, or infinitesimal bits of length, and we can use them together to get an infinitesimal bit of area. So let's say that this is a little bit of area, dA. Let's say that we have like a big plane or of area, and we want to break it up into little bits. And this has a little width, dx, and a little bit of depth, dy. And so the magnitude of the little bit of area is just dx dy, because we're just going to think of this as a tiny square. And then finally, let's say that I want to do a little bit of volume. So I just think of a cube, and the cube has a little bit of width dx, a little bit of depth dy, and then a little bit of height dz. And so we're going to call our little bit of volume d tau. This is another Greek letter, tau. And so our little bit of volume d tau is just dx dy dz, because this is a little cube. So in Cartesian coordinates, this is not too challenging. It becomes a little bit more challenging in cylindrical and spherical coordinates. One of the reasons it's more challenging is that phi, theta, and phi again don't actually have units of length. And you'll see what I mean about that in a second. So let's think about what would happen in a cylinder. So we have our cylinder, and I want to find a little bit of the volume of the cylinder. So I'm just going to draw the little bit of volume here. So I'm making a little patch that's approximately a square. It's got some curves to it. And then I'm moving into the cylinder a little bit to make a little cube. So let's figure out what are the lengths of this little cube. Well, it's got some height, dz. That's just exactly the same as in the Cartesian case. And it's got some depth, like it's going into the cylinder. So if it's going into the cylinder, then its little bit of depth is going to be d eta. And then the last coordinate here is the last side is the trickiest, and that's its little bit of width along, I guess we could say, the surface of the cylinder. Although this doesn't have to be at the surface, it could be somewhere inside the cylinder. And this is an arc length, which is to say that we can imagine it as a fraction of the circumference of a circle if we're looking right down on the cylinder. And this arc length has a length eta d phi. Because normally an arc length would be the radius at which the arc is occurring times the angle it sweeps through. And so here it's occurring at a radius eta, and it sweeps through a little bit of angle d phi. And so this little cylindrical volume element, d tau, is just eta d eta d phi dz. And you can see eta is a length, z is a length, phi is just an angle, but eta times d phi is now also a length. So this little volume element does have dimensions of length cubed, which is what we need it to have. Now, one concern you might have is that this is definitely not a perfect cube, because we know that we have these curving elements, these arc lengths, and also as we get deeper into the cylinder, those arc lengths are going to get a little smaller. We are saying that because d eta, d phi, and dz are so small that the actual curves are almost flat. And so treating this just like it's a cube is essentially a perfect approximation as long as we assume that d eta, d phi, and dz are small enough, which we will be assuming whenever we are setting integrals up in this class. Finally, let's do the spherical situation. It's going to be a little more complicated than the cylindrical situation. So we're going to have our set of axes, which we're going to put at the center of our sphere. We don't really need that set of axes actually for this because we don't really care about x and y, we just care about our coordinates. So we're going to have the center of our sphere, and at some location from the center of our sphere, yeah, we're going to have our little volume element. Again, we'll just do volume. So it's going to have some width along the azimuthal direction of the sphere, some height along the polar direction of the sphere, and then some depth along the radial direction of the sphere. So I don't know if I've drawn this perfectly, but those lines are supposed to be going in towards the center of the sphere. So not quite perfect. Now, these lines, the lines of depth going in towards the center of the sphere, are just going to have a length dr. So that's our easiest length here, the infinitesimal little bit of radius. Now we have two arc lengths. The polar arc length is just going to be r d theta. So this is very similar to the arc length on the cylinder. It's just the radius that this is at, so this is at some radius r, times the little bit of angle d theta that we're going down in the polar direction. The arc length in the azimuthal direction is a little more complicated. So we have to remember that whenever we're considering the azimuthal motion in spherical coordinates, we're considering a projection down into the xy plane. And so the radius of this little bit of volume, when it's projected down into the xy plane, it's at a radius r sine theta, and then it sweeps through a little bit of angle d phi. And so the cylindrical volume element, d tau, is r squared, because I'm picking up r's from both of these arc lengths, r squared sine theta d phi dr. So again, sine theta d phi and d theta don't have units of length, but they are both multiplied by an r, which gives them units of length, and dr itself has units of length. So we can see that our final cylindrical volume element, d tau, has all three factors of length that we need to make it a valid volume. And so you can use combinations of these little bits of path length in the r, theta, and phi directions to construct different area elements. So for example, if we want to think about a little bit of the area of the surface of a sphere, that would be r d theta times r sine theta d phi. And you can get some practice with this on your worksheet.